Welcome to this solution walkthrough for LeetCode problem number 1345, Jump Game 4. In this problem, we explore how to minimize the number of jumps needed to traverse an array, where jumping is influenced by both the array's values and indices. Let's dive into the problem and break down the solution step by step. In this problem, you are given an integer array called ARR. The goal is to start at the first element, which is at index 0, and figure out the minimum number of steps required to reach the last element of the array. You can move between indices based on three key rules. First, you can jump to the next index, which is I+1, as long as it exists. Second, you can jump to the previous index, I1, if it exists. Finally, you can also jump to any other index j where the value at ARR I is equal to the value at ARR j, as long as j is not equal to I. If it's not possible to reach the last index, you would return -1, though the problem guarantees that the end is always reachable. Your task is to determine the minimum number of steps required to achieve this goal. For example, consider the input array ARR equals 100 minus 23 minus 23, 100, 23 minus 23, 100, 100, 100 minus 23. The output for this example is 3 steps. Here's how the steps work. You start at index 0, where the value is 100. From there, you can jump directly to index 3, because the value 100 appears at that position as well. That's the first step. Next, from index 3, you can jump to index 7, which is another position with the value 100. That's step 2. Finally, from index 7, you jump to index 9, which is the last index in the array. This makes it a total of 3 steps to reach the end. The key to solving this example is recognizing that you can leverage the ability to jump to any index with the same value, which allows you to skip over large sections of the array. Now, let's look at another example. If the input array is ARR equals 7, 6, 9, 6, 9, 6, 9, 7, the output is just 1 step. Here's why. Starting at index 0, where the value is 7, you can jump directly to index 7, which is the last index in the array. This is because the value 7 also exists at index 7, and the rules allow you to jump to any index with the same value. Since you reach the last index in a single move, the total number of steps required is just 1. This example highlights how the ability to jump to matching values can sometimes lead to the most efficient solution. In a simpler case, if the input array is ARR equals 6, 1, 9, the output is 2 steps. Here's how it works. You start at index 0, where the value is 6. From there, you make your first step by jumping to index 1, which is the next index. Then, for your second step, you jump to index 2, which is the last index in the array. Since there are no repeated values in this example, you can only move to adjacent indices. This demonstrates how the problem can still be solved even when the array lacks opportunities for value-based jumps, though it may require more steps. Finally, let's consider some edge cases and constraints. If the array contains only one element, such as 7, then the start and end indices are the same, so no steps are required, and the output is 0. On the other hand, if all elements in the array are unique, like 1, 2, 3, 4, you can only move between adjacent indices, resulting in a linear traversal. For instance, the output for this example would be 3 steps. However, if all elements in the array are the same, such as 5, 5, 5, 5, you can jump directly to the last index in 1 step, giving an output of 1. Lastly, because the array size can go up to 50,000, the solution must be efficient to avoid excessive time complexity. These constraints ensure that the algorithm is robust and can handle both small and large inputs effectively. To solve problem number 1345, Jump Game 4, the goal is to find the minimum number of jumps required to reach the last index of the array. The challenge lies in the flexibility of the jumps allowed. You can move to the next or previous index, or jump to any other index that has the same value as the current index. This creates a graph-like structure where each index in the array is treated as a node, and the possible jumps form edges between these nodes. With this in mind, the problem becomes one of graph traversal, where we aim to navigate from the first node to the last node in the fewest steps possible. To tackle this, we evaluated multiple approaches, each leveraging this graph representation in distinct ways. The first approach considered was the brute force method. Here, the intuition is straightforward: for every index, attempt all possible jumps, whether to adjacent indices or to indices with the same value, using either recursion or iteration. This can be implemented using depth-first search, DFS, or breadth-first search, BFS, to explore all paths in the graph. However, this approach is highly inefficient, with exponential time complexity, as nodes may be revisited multiple times without optimization. In the worst-case scenario, the complexity can reach 2 to the power of n, making it unsuitable for large arrays. To overcome these inefficiencies, we can use an optimized BFS approach. This method involves exploring the graph level by level, ensuring that we prioritize paths with the fewest jumps. By grouping indices with the same value in a hash map, we can efficiently handle these connections. The hash map is created by pre-processing the array, mapping each value to the list of indices where it occurs. During the BFS traversal, we explore adjacent indices and use this hash map for quick access to indices with matching values. Once all indices for a specific value are processed, the corresponding entry in the hash map is cleared to avoid redundant computations. This optimized BFS has a linear time complexity of n, as each node and edge is processed only once, making it significantly more efficient than the brute force approach. Despite the advantages of optimized BFS, we also considered an alternative, bidirectional BFS. The key idea here is to perform BFS from both the start and the end of the array simultaneously, reducing the search space by focusing on the overlap between the two searches. Similar to the optimized BFS, this method uses a hash map for efficient jumps between indices with the same value, and maintains two queues for forward and backward exploration. The search terminates when the two queues meet, indicating that a path has been found. While bidirectional BFS can be faster than single-source BFS for dense graphs, its benefits are limited in sparse graphs like this one. Additionally, the implementation is more complex, requiring careful synchronization of the two searches. As a result, while this approach is theoretically appealing, it may not offer practical advantages for this specific problem. Ultimately, the optimized BFS with a hash map was chosen as the final strategy due to its combination of simplicity, efficiency, and suitability for this problem. Key insights that make this approach effective include grouping indices by value in the hash map, which allows efficient processing of jumps between indices with the same value, and clearing value groups from the hash map once processed to eliminate redundant exploration. By using BFS, we ensure a level-order traversal of the graph, meaning the first time the last index is reached, it is guaranteed to be with the minimum number of steps. This method strikes a balance between performance and clarity, achieving n, time and space complexity. While bidirectional BFS offers theoretical advantages in certain cases, its added complexity is unnecessary for this problem's sparse graph structure. Brute force, on the other hand, is infeasible due to its exponential time complexity. Thus, the optimized BFS provides a scalable and clear solution, making it the ideal choice for solving jump game 4. To solve the problem of determining the minimum number of jumps required to reach the last index of the array, we start by framing it as a graph traversal task. The key idea is to use breadth-first search, or BFS, for its efficiency in finding the shortest path in an unweighted graph. First, we initialize the algorithm by creating a graph representation of the array. Each value in the array is mapped to a list of indices where that value appears. This mapping enables quick access to all positions with the same value, which can be treated as direct jumps. Next, we set up a queue for the BFS, where each element is a tuple containing the current index in the array and the number of steps taken so far. Additionally, we use a visited set to track indices that have already been processed. This prevents cycles and avoids redundant computation. Finally, we handle an edge case. If the array contains only one element, no jumps are needed, and the result is simply 0. The BFS traversal begins at the first index, which is initialized in the queue along with a step count of 0. The traversal proceeds as long as the queue is not empty. For each step, we dequeue the current index and check if it corresponds to the last index in the array. If it does, we immediately return the current step count because the shortest path has been found. If not, we explore all possible neighbors of the current index. These include the next index, the previous index, and all other indices that share the same value as the current element. For each valid neighbor that has not been visited yet, we add it to the queue and mark it as visited. To further optimize the process, we clear the list of indices for the current value in the graph after processing it. This ensures that we don't revisit these indices in the future, thus avoiding redundant jumps. If the BFS finishes without reaching the last index, which the problem guarantees won't happen, we would return -1. The algorithm relies on several key insights to achieve its efficiency. First, representing the array as a graph where values map to their indices allows constant time access to all positions with the same value, eliminating the need to repeatedly scan the array. Second, BFS is particularly well suited to this kind of problem because it systematically explores all possibilities level by level, ensuring the shortest path is found. The level of the BFS corresponds directly to the number of jumps taken. Another important optimization is clearing the processed values from the graph once their indices have been used. This ensures that we don't revisit or reprocess indices unnecessarily, which greatly improves runtime efficiency. Finally, the visited set plays a crucial role in preventing cycles and redundant work, ensuring that each index is processed only once. Together, these strategies allow the algorithm to operate efficiently even for large arrays. The algorithm makes use of three primary data structures. The first is the graph, which is implemented as a dictionary. Each key corresponds to a value in the array, and its associated value is a list of all indices where that value appears. This facilitates direct jumps between indices with the same value. The second data structure is a queue, implemented using a deque. Each element in the queue is a tuple containing the current index and the number of steps taken so far. The queue enables the BFS traversal, allowing us to systematically explore all possible paths. The third data structure is the visited set, which stores indices that have already been processed. This prevents revisiting indices and ensures that the algorithm avoids unnecessary work. In terms of complexity, the time complexity of the algorithm is O(n). Constructing the graph takes O(n), and each index and value is processed at most once during the BFS. The space complexity is also O(n), as the graph, queue, and visited set each require linear space. Let's walk through an example to see the algorithm in action. Consider the input array 100, -23, -23, 100, -23, 100, 100. First, we construct the graph representation. The value 100 maps to the indices 0, 3, 5, 6, and the value -23 maps to 1, 2, 4. Next, we initialize the BFS with the queue containing 0, 0, representing the starting index and 0 steps. The visited set initially contains only the first index, 0. During the first BFS iteration, we process index 0 with 0 steps. From here, we add the next index, which is 1, to the queue and mark it as visited. We also add all other indices with the same value, 100, which are 3, 5, 6, to the queue. These indices are marked as visited, and their list is cleared from the graph to prevent future redundant processing. The graph now only contains the value -23. Continuing the BFS, we process index 1 with 1 step. From here, we add the next index, 2, to the queue and mark it as visited. Similarly, we add index 4, which shares the same value of -23, to the queue and mark it as visited. After processing these, the list for -23 is cleared from the graph, leaving it empty. Finally, we process index 6 with 1 step. Since index 6 is the last index of the array, we terminate the BFS and return the step count, which is 1. This example demonstrates how the BFS systematically explores the shortest path to the last index, leveraging the graph representation for efficient jumps and the visited set to avoid redundancy. The result, 1, represents the minimum number of jumps required to reach the end of the array. Here, we start by importing the necessary modules, default dict and deque from the collections library. These will help us efficiently manage the graph structure and the queue for our breadth-first search, or BFS. Next, we define the solution class and the method minJumps, which takes an input array ARR. The first check handles the edge case where the array length is 1 or less. If that's true, no jumps are needed, so we simply return 0. After that, we build a graph where each unique value in the array maps to a list of indices where that value occurs. This will allow us to quickly find all indices with the same value, which is a key part of optimizing our jumps. Next, we initialize the BFS process. We start by adding the first index, 0, to the queue, marking it as visited, and setting the step counter to 0. The while loop then begins, and it will continue as long as there are indices to process in the queue. Within the loop, we iterate through the current level of the queue. For each index being processed, we first check if it's the last index of the array. If so, we've found the minimum jumps required, so we return the step count immediately. Now we move on to explore the neighbors of the current index, which include adjacent indices as well as all indices with the same value. The neighbors are calculated by combining the list of indices with the same value as the current index, using the graph, along with the adjacent indices, one step forward and one step backward. For each neighbor, we first check that it's within the bounds of the array and hasn't already been visited. If it meets these conditions, we mark it as visited and add it to the queue for further processing. This ensures that we only process each index once, avoiding redundant work. Additionally, to prevent unnecessary reprocessing of indices with the same value, we clear the graph entry for the current value after processing its neighbors. This step is crucial for optimizing performance, especially when dealing with large arrays with repeated values. After processing all neighbors for the current level, we increment the step counter, as this represents moving one level deeper in the BFS. If the while loop exits without finding a solution, we return -1 to indicate that reaching the last index is not possible, though this scenario is unlikely given the problem constraints. This concludes the implementation of the minJumps function. Here, we start by importing the necessary libraries and defining our solution class. The first method, minJumps, takes an array as input. If the array length is 1 or less, we immediately return 0, as no jumps are needed. Next, we create a hash map called graph to map each unique value in the array to a list of indices where that value appears. This allows us to efficiently find all indices with the same value later. We populate this map using a loop through the array. After building the graph, we initialize a breadth-first search, or BFS, starting from the first index. A queue is used to manage the BFS, and we mark the first index as visited to avoid revisiting it. We also initialize a variable steps to track the number of jumps. The while loop continues as long as there are indices to process in the queue. Inside the loop, we process each index at the current BFS level. At this point, we check if the current index, cur, is the last index of the array. If it is, we return the number of steps taken so far, as we've successfully reached the end. If not, we explore the neighbors of the current index. Neighbors include indices with the same value, as stored in the graph, as well as the adjacent indices, cur1 and cur+1, if they are within bounds. We loop through all the neighbors and add any unvisited indices to the queue. These indices are marked as visited to prevent revisiting them. After processing the neighbors, we clear the entry in the graph for the current value to avoid redundant checks in the future. Once all indices at the current BFS level are processed, we increment the step counter and continue to the next level. Finally, if the BFS completes without reaching the last index, we return -1, indicating that it is not possible to reach the end of the array. This ensures that the function properly handles edge cases where a solution does not exist. With this implementation, we efficiently use BFS to find the minimum number of jumps required to reach the last index, leveraging the graph to quickly access indices with the same value. To solve this problem, we start by building a graph where each unique value in the array maps to all the indices that contain that value. For the input array, 100, -23, -23, 100, 150, -23, the graph is constructed as follows: 100 maps to indices 0, 3, 4, -23 maps to 1, 2, 6, and 50 maps to 5. Next, we set up a queue initialized with the starting index 0, a visited set to keep track of indices we've already processed, and a steps counter, which starts at 0. Now, in the first step, the queue contains just the index 0. From here, we dequeue 0 and explore its neighbors. These neighbors include indices with the same value 100, which are 0, 3, 4, as well as adjacent indices -1 and 1. Since -1 is invalid, we add valid neighbors 3, 4, and 1 to the queue and mark them as visited. After this step, the graph entry 4100 is cleared to prevent revisiting these indices, and the queue is updated to 3, 4, 1, while the visited set becomes 0, 1, 3, 4. Now we increment the steps counter to 1. Moving on, the queue now contains indices 3, 4, 1. We dequeue 3, and its neighbors include indices with the value -23, 1, 2, 6, as well as adjacent indices 2 and 4. From these, valid neighbors 2 and 6 are added to the queue and the visited set. The graph entry 4-23 is cleared, and the queue is updated to 4, 1, 2, 6, with the visited set now 0, 1, 2, 3, 4, 6. Again, we increment steps to 2. For the second example, the input array is 7, 7, 7, 7, 7. Here, we first build the graph, which maps the value 7 to all of its indices 0, 1, 2, 3, 4. The queue is initialized with index 0, and the visited set starts as 0. The steps counter is again set to 0. For the first step, we process index 0. Its neighbors include adjacent indices -1 and 1, as well as all other indices with the value 7, which are 0, 1, 2, 3, 4. From this, valid neighbors 1, 2, 3, and 4 are added to the queue. The graph entry 47 is then cleared to avoid revisiting these indices. At the end of this step, the queue becomes 1, 2, 3, 4, and the visited set is updated to 0, 1, 2, 3, 4. The steps counter is then incremented to 1. Next, we dequeue 4 from the queue. Since 4 is the last index in the array, we immediately return the result as steps plus 1, which gives us a total of 1 step. In the third example, the input array is 6, 1, 9. The graph here maps 6 to index 0, 1 to index 1, and 9 to index 2. We initialize the queue with index 0, the visited set is 0, and the steps counter at 0. For the first step, we process index 0. Its neighbors include adjacent indices -1 and 1, as well as other indices with the value 6, which is just 0. From this, we add the valid neighbor 1 to the queue and mark it as visited. The queue is now 1, and the visited set becomes 0, 1. We then increment steps to 1. In the next step, we dequeue index 1. Its neighbors include adjacent indices 0 and 2, as well as other indices with the value 1, which is 1. From this, we add the valid neighbor 2 to the queue and update the visited set to 0, 1, 2. The queue now contains 2. Finally, we process index 2. Since 2 is the last index in the array, we return the result as steps plus 1, giving us a total of 2 steps. The time complexity of our solution can be broken down into 2 main components. First, we have the graph construction step. Here, we iterate through the array to build a mapping of each unique value to the list of indices where that value appears. This is done in a single pass through the array, making it an O(n) operation, where n is the length of the array. Next, we have the breadth first search, or BFS, which processes each index and its neighbors. Neighbors include adjacent indices as well as indices sharing the same value. Accessing these same value neighbors takes constant time per lookup, but clearing the list of indices for a value takes time proportional to the number of indices associated with that value. Across all BFS operations, clearing these lists sums to O(n), since each index belongs to only one list. Similarly, checking and adding adjacent indices occurs in constant time for each index. Since each index is visited at most once and all operations involve sum to O(n), the overall time complexity of BFS is O(n). Adding the components together, the overall time complexity of the solution becomes O(n) for graph construction plus O(n) for BFS, which simplifies to O(n). Now let's analyze the space complexity. The first consideration is the space required to store the graph. This graph maps each unique value in the array to a list of indices. In the worst case, if all values are distinct, the graph will store n entries, each associated with one index. Conversely, if all values are the same, the graph will store a single entry with n indices. In both cases, the space used by the graph is O(n). Then, we have the visited set, which tracks the indices we've already processed. Since we visit each index only once, the size of this set is at most n, contributing another n to the space complexity. Next, we consider the space required for the BFS queue. This queue holds indices that are waiting to be processed. In the worst case, the queue could grow to include all indices in the array simultaneously, which would require n space. When we combine these components, the graph, the visited set, and the BFS queue, the overall space complexity of the solution is n. To complete our analysis, we can look at the algorithm's behavior in different scenarios. In the best case, the array contains only one element, such as 0. Here, the algorithm immediately returns 0, with both time and space complexity of 1. In the average case, the array contains a mix of repeating and distinct values, requiring BFS to explore a moderate number of neighbors. In this scenario, both the time and space complexity are n. The worst case occurs when all elements in the array are identical, such as 7, 7, 7, 7. Here, BFS processes all n indices, and both time and space complexity remain n. Now, let's compare this optimized solution to a brute force approach. A naive method would involve recursively exploring all possible paths to the last index. This would result in exponential time complexity, as each index would lead to multiple recursive calls. For example, in an array like 1, 1, 1, 1, the number of recursive calls would grow exponentially with the size of the array. Specifically, the brute force approach has a time complexity of 2 to the power of n, and a space complexity of n, the latter due to the recursion stack depth. In contrast, our optimized BFS-based solution reduces the time complexity to n, and the space complexity to n. This efficiency is supported by the proof of big O. The graph is constructed in n by iterating over the array, and BFS processes each index and its neighbors once, summing to n operations. Clearing graph entries ensures each values list is processed only once, contributing n in total. Therefore, the time complexity is definitively n, and the space complexity is dictated by the graph, visited set, and queue, each requiring n space. When tackling jump game 4, one of the most frequent missteps is failing to treat the problem as a graph traversal. Each index in the array can be seen as a node, and valid jumps create edges between these nodes. By not using breadth-first search, which is highly effective for finding the shortest path, solutions often devolve into brute force, exploring every possible jump. This leads to exponential time complexity and inefficiency. Another common issue is revisiting indices unnecessarily during BFS. Each index should be marked as visited once it's processed to avoid redundant computation or even infinite loops in edge cases. Lastly, the problem allows jumps to indices with the same value, but if you don't optimize this, it can become a major bottleneck. For example, repeatedly jumping between indices with the same value is wasteful. Once you've used all duplicates, it's best to clear the list to avoid unnecessary work and speed up the algorithm. Another common mistake is ignoring constraints when jumping to I1 or I+1. If you allow jumps to indices outside the bounds of the array, like negative indices or those beyond the last index, you'll encounter runtime errors or incorrect results. This is especially critical in edge cases, such as arrays of size 1 or arrays with all identical elements. For instance, if the array has only one element, the correct answer is 0 since no jumps are needed. Overlooking these special cases can lead to incorrect results or unnecessary computations. Ensuring your solution explicitly handles these scenarios is key to building a robust implementation. This problem is best approached as a graph traversal, where the indices of the array are nodes and the valid jumps form edges. Given this setup, BFS becomes the optimal search strategy because it efficiently finds the shortest path, or minimum number of jumps, required to reach the last index. While DFS is possible, it's less suited for this problem since it explores paths deeply before backtracking, often leading to redundant work and inefficiency. Another critical optimization is clearing the list of indices with the same value after processing them. This prevents revisiting nodes unnecessarily and keeps the time complexity manageable. Speaking of efficiency, the optimized approach operates in n time, as each index and value is processed at most once. During interviews, it's crucial to clearly articulate why BFS is ideal and how you've designed your solution to avoid redundant computations. Jump Game 4 has several related problems that share similar concepts. For example, in LeetCode 45, Jump Game 2, the goal is to find the minimum number of jumps to reach the last index, but without the added complexity of jumping between indices with the same value. LeetCode 1306, Jump Game 3, asks whether it's possible to reach an index with a value of 0 starting from a given index, which also requires careful handling of valid jumps. LeetCode 55, Jump Game, is another variation where you determine if reaching the last index is possible with the allowed jumps. Lastly, LeetCode 542-01 Matrix is a BFS problem that involves finding the shortest distance from each cell to the nearest zero. Understanding these related problems can deepen your grasp of graph traversal techniques and help you recognize patterns across similar challenges. While BFS is the preferred approach for Jump Game 4, alternative strategies exist, each with its own trade-offs. Depth-first search, or DFS, can be used, but it's less efficient for finding the shortest path because it explores one path fully before backtracking. This can lead to exponential time complexity in the worst case. Another option is bidirectional BFS, which starts the search from both the first and last indices and meets in the middle. While this approach can reduce the search space, its implementation is more complex and doesn't necessarily provide significant benefits for this specific problem. Finally, dynamic programming, or DP, is another potential solution. It involves tracking the minimum jumps to each index, but it's less intuitive and harder to optimize compared to BFS. Additionally, DP typically requires more space to maintain the table, making it less efficient overall for this problem. Great job following along. We tackled Jump Game 4 using BFS and optimized it with a hash map for grouping values. Remember, BFS is a go-to approach for shortest path problems, and hash maps can save you significant computation time. Thanks for joining, and don't forget to like, share, and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!